All right, there we go. Hello, everyone. You're in the 8th week. Let's just start our lecture. Share the screen with you. Okay, optimization model with integer variables. We kind of did this in the network optimization problem, but network optimization problem is kind of an integer variable or integer programming models that are special. That's why we give them their own space for optimization, but they're going to finally technically be under the integer models, integer programming. So today, specifically, we're going to talk about a specific kind of integer models, which variable can be only binary. And a binary variable is an integer variable that takes only 0 and 1. It's yes or no. It's black and white. Okay. So it has only two possibilities. Either you invest in an investment or you don't. Either you take a job or you don't. Either you build a building or a hub at some place or you don't. So these kind of problems. We could have also a combination of these. So if you have some variables that are continuous, but some of them, at least one of them, is integer or binary, we are still going to call them integer models because they are not going to be able to be solved by generally with the simplex linear program or approach. Some people call them mixed integer programming if you have a combination of continuous and integer variables. But nonetheless, they are they can't be solved with the same approach that we used to solve the continuous problems, the simplex method. If you remember from the last lecture, there are special kinds of under certain scenarios. Some of these problems, the integer problems, can be modeled as a continuous linear program. That means that you can actually waive or relax the integrality constraints and do not enforce them to be integer because of certain conditions. And there is actually a proof for a theorem under mathematical programming in mathematics for that can prove that under certain condition, you can just relax the integrality condition of the variable to be integer and solve them using simplex algorithm. But that's a special case, and it's not generally true. So x, if it's a binary, it can take 1 if or it can, for example, you invest in an investment or you don't, so 0 or 1 only. All right, so integer programs are generally harder than the continuous programs because the additional constraint that they have, in addition to constraint that you have for a general mathematical program, you have to also enforce a condition on the variables to be whole numbers, and they can't be fraction. So that's going to add more complexity to the program or the problem. That makes it harder to solve. And the problems that we solve here in class, the examples that we do, we call them generally toy problems because they are so small in size that they are like a toy. So you don't see a real clear difference between the solution time or the time that Excel takes to solve the problem. But believe me, when you solve a real problem, it's gonna you're gonna see the impact. For example, a continuous large problem can be solved within a couple of minutes, and an integer program can be solved within hours, like 20 hours, with like a fast computer, not a supercomputer. But anyway, even supercomputers cannot afford for our problems to do them in seconds or minutes. All right, so the problem that one of the problems that we're gonna solve and work on for an example of binary variables or integer variables, integer models, is capital budgeting problem. So suppose that you have a fixed amount of money, say in this example, you have $15 million. You have 7 options of investment to invest in. And the data shows us that these investments are different. They have different requirements. For example, they have different costs and they have different return on investment, or as what we have here, using the return on investment present value of that. So take a look at this table here. On the column, you see the 7 different investments. The first row shows the cost of that investment. That's $1 million. For example, the first investment cost $5 million. The second investment $2.4 million, etc. And the second row shows the net present value, and that's actually based on what in present value, what would be the return of investment, would be including your capital. So for example, you invest $5 million and you get $5.6 million back. For investment 2, you invest 2.4 million and you get 2.7 million back, and so on and so forth. So based on this, you can actually compute the return on investment. That's going to be the NPV minus cost divided by cost. For example, 5.6 minus 5 divided by 5, that's actually 12%. The key condition here is that this is an integer or a binary variables model, and that means that you can invest in an investment or you just don't. That means that you cannot, for example, invest 50% going in, 50%, just 50%, or 40%, or 60%. That means that you cannot invest fractionally. You either invest or you don't. For example, you're either going to go and spend $5 million and invest in investment 1, or you don't. So you cannot, for example, spend $2.5 million and invest 50% in investment 1. So it's a binary kind of issue. You either do or you don't. What is the goal? The goal is actually find the best combination of this investment to invest in so that you maximize your NPV, total NPV, based that you only have $15 million to invest. So you might actually, if you think about it, you might be thinking that, okay, if you look at investment 4 and investment 6, they have the largest return on investment. So it kind of looks natural and logical to invest in those. But as you're going to see in our final solution, the optimal solution is not actually like that. So this is not like an intuitive problem. This problem is called the knapsack problem in mathematics, the mathematical programming community. And because this is similar to a case where you have a knapsack, and your knapsack, actually every knapsack has a fixed capacity or fixed weight that you can put item in it. Okay, so for example, you can only put 20 pounds of items or 40 pounds of items in the knapsack, and you have, say, I don't know, 20 different items that you can pick from, but they have different value to you, utility value, and they have different weights. So what you want to do is, based on the limitation on the capacity or the weight of the knapsack, you want to pick the items from those 20 or 100 items that would maximize the utility and still stay within your capacity. So that's why it's called the knapsack problem. There are different actually interpretation of these with different names and application that we're going to talk about. So this is the influence chart. I don't think we no longer need actually influence chart. This sounds too easy, but just in case, the total NPV of investment, that's our output that we want to maximize. So for that, we have an input, and that's the NPV for each investment. That's an input, so that's why we have it in blue color. And also it depends whether we invest in an investment or we don't. So that's our decision variable. So also that also matters. And our decision variable would also define or decide the total cost of our investment, which would be impacted by the cost of each investment, which is also it's by itself an input and blue color. And that has to be less than the budget that we have for investment, which is an input. So it's a pretty simple problem. Right, so how to formulate this problem in Excel? I have already published, as I told you in email, all the class material that I'm using here, Excel files, the slides on iLearn. So there are 7 binary variables for our problem, and that's for 7 investments. For each investment, you want to see whether you would invest in investment. Say X1 stands for whether you invest in investment 1 or not. So X1 would be 1 if you invest in investment 1, and X1 would be 0 if you don't. So there will be 7 binary decision variable. And the total cost and total NPVs, we're going to use the sum product for that to compute it. There's only one constraint for that, and that's the capacity of your knapsack, or here the budget that we have. So we're going to go to Excel to solve this problem. Okay. So I'm going to rename this cell, this sheet, to model. I'm going to put larger, and I'm going to actually name the problem here. And here are going to be our data. I'm going to copy the data here. Okay, so these are our data. You see our 7 investment, the cost of each investment in $1 million, and NPV, the ROI. And you can see how ROI are computed. So ROI is, for example, investment 1 is equal to 5.6 divided by 5 minus 5, and then divided by 5. Right, so what else do we need? We need our decision variable. I'm gonna decisions. We're gonna have 7 decisions under these values. I'm gonna use the decision, my decision is started here. Okay. We can actually name our some of the things that we have here. We can bring names to them, the decision, the cost, and NPV. And now we're going to go to the constraints. Okay, budget constraints. So what is the budget constraint? The budget constraint says that the total cost of investment must be less than or equal to, I'm just going to copy the budget. Okay, so here the total cost of investment, that would be the sum product of our decisions by cost. And that has to be less than equal to the budget, which is 15. And 15 is input, so I'm going to use input here. Okay, and what else do we need? We need the objective function. We only have one constraint here, so we need the objective function. The objective function would be objective function. And that would be the total. So this time, some product, our decisions, and the average investment. So this is going to be our output. So I'm going to use output style. Okay, so there we go. We can actually test our investments. So I'm going to say here 0. I'm going to, let's actually pick the largest ROI here. This one, also this one. So that's 11.9. And the budget is met. That's 10.5. So I can actually pick, I can pick this one. I can pick this one. So this one too. 14.6. Can I go here? I can't pick this one. I can't pick this one either. So that's the best I can do here. Okay, so this is just my random solution here. The random solution is to pick invest on investment 2 and 4 and 6, and you're gonna get $14.6 million on your total NPV, and the cost we have used 12.9 of it. So let me also name this and name these two. Check on these. Okay, budget, cost, decision, NPV, total cost of investment, and total. Looks like good. So let's go to the data ribbon, the data tab here, and the solver, and put it in the solver. So I'm going to put the total NPV here, and we want to maximize this, and our decision variables are these values here. I'm going to add the constraints here. We have only one constraint, and that this has to be less than equal to this one. And we need one more constraint, and that's the binary constraint. That means we have to tell the solver that our decision variables, x1, 2, 3, 4, 5, 6, 7, has to be binary. So I'm going to say these, and from here, I'm going to click and solve BIN. That means that these values has to be binary. Okay. I'm going to click OK. Picked everything. The names are also shown here. We are maximizing the total NPV by changing the decision variables. We have decision has to be binary, and the total cost of investment has to be less than the budget. We make sure that the variables are non-negative. We're going to pick simple XLP, but we're going to make sure that because this is an integer programming model, we're going to make sure that the integer optimality that's 0. So it's going to find the best optimal solution, not just the close one. So 100% optimality. Click OK here. So just take a look at the values that we have here. This is just a random value, the random solution that I just put here. investment 2, investment 4, investment 6, and my objective function right now is 14.6. So let's see if the optimization can give us a better solution. So as you can see here, it was fast. It just solved it instantaneously because this is a binary models or integer model. You don't see the sensitivity report here on the report side. Okay, so I'm going to click OK here. This is going to be our optimal solution. So our optimal investment is to invest on investment number 2, number 3, and number 4, and number 7. So as you can see here, we do not invest on investment 6, although its rate of return is 13.3, which is equal to the rate of return of investment 4, and it's also cheaper, as you see here. So this is a non-intuitive actually solution. Although I have to say, this problem has more than one optimal solution. That means that you're not going to get any solution of investment that you would get a total NPV larger than 16.7. But you could get a different combination of these with the same total NPV, okay, because this problem has more than one solution. So if you try this and you get different solution than this that I have here, it's fine because we have more than one optimal solution. We're going to see a couple of them here, but you cannot get any solution with a better optimal objective function or better or larger total NPV. Okay. So now we're going to do some extension to this problem to give you a better idea how to handle different scenarios, different situations when you could face in real life in your job. So I'm going to stop share here. I'm going to open the. Okay, let's do this. We need to do sensitivity analysis here. Okay, so optimal solution, it's not an obvious solution as you saw here. It's not based on the highest ROI, as I said, so it's not a solution. It's not unique. We're going to have multiple solutions, as I'm going to show you. So we're going to do a sensitivity analysis, and we're going to see the impact of the budget. So we assume that the budget was 15 million here. We want to see how would that affect and impact your optimal investment and your total NPV. So let's do that. Let's actually use the solver table to do that. So I'm going to go to solver table here. I'm going to run it. Yes, we have an active sheet here, and I want to run it one-way table. I'm going to pick the input cell as my budget here, and I'm going to name it budget. And we're going to go from 15 to 25 by 1. 15, 25 by increment of $1 million. And what I want to see is the investment and the total NPV. So we're going to create a new sheet here. As you see here, it takes quite time to solve this problem. So this is our investment 1, investment 2. So I don't think I would need to rename this. The kind of obvious here. Just want to center them. And these are our budgets that changes from 15 to 25. Let me first check the total NPV graph here. So as you see here, as our budget on the x-axis increases, almost linearly, our total NPV on the y-axis increases as well. But this is not exactly.
Professor, it's not The screen hasn't shared yet.
It's not shared. Do you see it now?
No, it shows started screen sharing, but it doesn't show anything.
It's coming through for me.
Yeah, it's coming out for me too.
Yeah, I can see it
Sensitivity
also.
model.
Okay, maybe it's just my internet. Sorry.
Okay. No problem. I hope it works for you. Okay. Yeah. So we can see also the how it would actually impact our optimal investment plan. As you see here, for example, when your budget is 15, you're not actually picking decision 1 or investment 1. But when you increase it up to 18, it becomes part of your investment up to 20. But interestingly, when the budget is 21, it's excluded from your optimal solution or optimal investment, but it's going to come back at 22. It's going to disappear at 23 and 24. So as you see here, there's not like a linear kind of relationship between that and the particular investment. The same goes for other investment plan as well, except for this, the investment 4. Investor 4 actually is always one of your optimal investment. And if you look at it, kind of makes sense for the 13.3% ROI, but look at the cost. The cost is $6 million, and it's actually more expensive than investment 6, which has the same ROI. So it's not kind of obvious, right? And so on and so forth. But the increment here, although it looks linear exactly, but it's not quite linear. So we can actually check here the difference between these two consecutive investments. So that's 1.2. If you drag it down, you can see that, for example, 1.2, 1.2, we have 1.1, 1.2, 1.9. So as you see, it's not exactly a linear line, but it's almost linear. Any question? Okay, so now let's go to the extension here. Do you see the PowerPoint? Everyone does see the PowerPoint? Do you see the PowerPoint?
Yeah, we see the PowerPoint.
Okay, so we're gonna do a couple of extensions. The first extension is we want to show you how to implement a certain condition or a certain scenario. So for example, what if actually you have kind of a certain condition on the number of investment? For example, you wanted to have at most 2 investment can be selected, or at least at most 3, or at most 4 or 5, or whatever number. Okay, at most say you're gonna go with 2. So how would you enforce that condition or scenario on your problem? So if it's, for example, at most 2 investment, then the summation of your investment, because they are both binary, has to be less than equal to 2. If it was 3, then it has to be less than 3. If it was B, it has to be less than B. Okay? So this is how you would do this condition. Another scenario is that, for example, say if investment so conditional investment or contingency investment. That means that if you invest in B, you also have to invest in C. This kind of scenario. So suppose that if you invest in investment number 2, you would have to also invest in investment number 5. But it doesn't work the other way. That means that if you invest in 5, you don't have to invest in 2. So if you invest in 2, you have to invest in 5. And this actually would do it because if investment 2 is selected, that makes X2 1, and X5 has to be greater than 1. So that means that X5 can have to be 1 because it only can be 0 and 1. But the other way, it doesn't have to be true. So for example, if X2 is not selected, X2 is 0, X5 still can be selected. Also, if X5 is not selected, that means if X5 is 0, then X2 cannot be selected. So it has this kind of relationship you can enforce and implement in your model. So we're going to do a couple of these. The third implementation or scenario is that suppose that you want to have a condition that the investment 1 or 7 or both has to be selected. That means that at least out of investment 1 or 7, one of them at least has to be selected or both. Okay, so you're going to say x1 plus x7 is greater than or equal to 1. That means that both of them cannot be 0. That means the scenario that none of them is selected is out of window. Okay, so the only acceptable scenarios are either x1 is 1 or x7 is 1 or both of them are 1. If you want to say, for example, you could actually add to this extension. For example, say out of in investment 1, investment 2, and investment 7, 2 of them has to be selected. Yeah, at least. So you're gonna put greater than or equal to 2. There are other actually scenarios as well. For example, the mutual exclusive option. That means that either x1 or x2 can be selected, and not they are both cannot be selected, and they are both cannot not be selected. Right? So that means x1 plus x2 has to be 1. That means okay, x1 has to be 1 or x2 has to be 1. Non x2 and x1 cannot both be 1, cannot both be 0 either. So this is different from the scenario that we had before. Or, for example, say out of 7 investment, you want exactly 5 of them to be selected, or k of them to be selected. So you're going to add them up and then make them equal to that certain number. So, for example, you want out of 7, you want to make sure that exactly 3 of them is selected. So the summation of them has to be equal to 3. So that's another how you would enforce or implement this conditional scenario. The last one is the threshold level. That means, for example, you want to make sure that x falls between a and b. So you can actually define another binary variable y, and then you're going to make sure that x is greater than or equal to a multiplied by y. So you want to make sure that x is going to be between a and b. It's a continuous variable and it's between a and b. So this is how you could actually enforce it. So you could say x is greater than or it could also be 0. So x is greater than or equal to a multiplied by y, and x should be less than or equal to b multiplied by y. So when y is 1, then x will be greater than a and less than b. That means that this will hold true. But when y is 0, then x has to be 0 too, okay? Because x has to be greater than 0 and less than 0. And the only possibility that is when x is equal to 0. So these are the scenarios that we can implement. So let's go ahead and actually apply the first one, for example. So I'm going to go back to the model and do that. Okay, so 2 of them, at most 2 of them can be selected. Okay. Extension 1. At most 2. Some of the investments has to be less than or equal to 2. And 2 actually here is, but here I'm gonna put here, for example, I'm gonna put, some of these just so what I have to do is I have to go to solver and add this constraint. So I'm going to add this constraint that this has to be less than or equal to 2. And click OK. Gonna solve. So it's 14.5. And if we change this, for example, to 3, we're gonna get different number. This one again. Okay. So I changed it, the 2 to 3. That means that at most 3 investment can be made. The total NPV is 16.7. When I made it to 2, it actually dropped to 14 point something. But when I made it to 3, it jumped back to the 16.7, which was the optimal one. So, but if you look at the our optimal investment, the solution actually changed. So we have a different actually investment. We have a different optimal solution with the same, of course, the same objective value. Okay, so that's why we say that this has more than multiple optimal solution. Here. Here. And I could go back to this and calculate this. And solve it again. So as you see here, this solution also is different from what we had before. Okay. But with the same objective value. Okay. All right, so let's do another extension. So suppose that we want to enforce this scenario where when investment number 2 is selected, investment number 5 has to be selected too. So extension 2. If 2, then 5. Plus 5. Okay, it's not sum. This is how we would have to apply it. I'm gonna get rid of these. This is 2. This is 5. This is equal to investment 2. And this is equal to investment 5. And because these two values are, I'm going to put them as decisions. All right, so let's now go to solver and add this constraint. I'm going to add this constraint that this has to be less than equal to this. Okay, so we actually got a different optimal investment with the same, of course, same objective value or same total NPV. So I'm going to copy this again here. Make sure that we have that. So far we have 3 different optimal investment plan with the same optimal total NPV. The next scenario, either investment 1 or investment 7 or both must be selected. That means x1 plus x7 must be greater than equal to 1. So let's that one. Extension 3. Either 1 or 7 or both. Okay. Investment 1 1 plus 7. Then I go with this 1 plus 7 has to be greater than 1. Insert so I'm gonna put investment 1 plus 7 here, and yeah, it's going to be an input and an output. Okay, so this is a calculus value, so I'm not gonna use the decision. Let's go back to solver, get rid of the last extension and change it. So I'm going to this and say this has to be greater than equal to this value. And I'm going to, right, so as you see here, we have yet another optimal solution with the same total NPV, of course. So I'm going to copy this and paste it here. Oh, it looks like the first and the third one are the same. Yeah. Okay. Okay, so far, 3 different optimal investment plans. Okay, any question? That was all for this investment problem.
Professor, would you mind repeating the constraints for extension 3 in the solver?
Okay. Let me find it. Great. Okay, so this is just the description. Okay, this is description. This is where I put it. So this is, let me get rid of this. It's a, we want to say, let me go back to the slide. So we want to say either investment 1 or 7 or both must be selected. Okay, so when you enforce, you have to enforce it like this: x1 plus x7 must be greater than equal to 1. That means that either x1 has to be 1 and x7 has to be 0, x1 has to be 0, x7 has to be 1, or both x1 and x7 has to be 1. Both of them cannot be 0 because 0 cannot be greater than 1. Okay, so this is how would be enforced: 1 plus 7 greater than 1. In this cell, I'm going to say investment decision variable x1 plus x7. Okay, and this has to be, this is just for description. Excel doesn't care if you know whatever you put here, if I put this here or not. This is just for us that we see this to better understand. Okay, so now I'm going to the solver. Let me get rid of this. Suppose that I want to add it. So I'm going to add this constraint. So I'm not going to do this. This is the label. This is the description. I'm going to say this cell, which is the summation of investment 1 and investment 7, x1 and x7, x1 plus x7, must be greater than or equal to 1, which is an input. It could be different value. So we solve and we find out.
Thank you so much.
Back here. So we did this extension. You don't have to do the rest, but that's how we would implement it. For mutually exclusive, which is just instead of say less than one to make it exactly equal to one. If you want to exactly select X out of N, here we have 7 number of investments. Say you want to pick exactly 5 of them, or 3 of them, or 2 of them. You can actually make sure that the summation of all these decision variables that are binary has to be equal to that value. But you have to make sure that this doesn't make your problem infeasible. For example, in our example, we only have 3 investments selected, or 4. So if you enforce this constraint that all of this has to be equal to 5, this actually doesn't have an optimal solution, because it doesn't have a feasible solution. So let me show you how this would work. So if the extension 5, so, exactly 5 investments. Okay. Sum of investments has to be exactly equal to say 5. Okay. So here I'm going to say sum of all of these, and here is the same. Then forget about this. Just for our understanding, I believe if you implement this, you might not necessarily get a solution. Add this constraint that this has to be exactly equal to 5. Add this. Let's see if it can solve it. Okay, so this is what we get. Solver could not find a feasible solution. Okay, so there is no combination of these investments, and that 5 of them can be selected, because the cost would be, the cost of the investment would exceed your budget. If you look at the cheapest investment, that's investment 2, investment 3, investment 6, and 7. So for example, 2 and 7, that's 5.4, plus the next one, which is 3.5, that's 8.9, almost 9. 9 plus 4.5, that's 13.5, plus whatever value that's going to exceed 15. So it's not going to be feasible. So you have to make sure that the constraint that you're going to enforce doesn't make your up to your problem infeasible. All right. Let's go to the next problem. All right, so this is yet another problem, integer model, fixed cost manufacturing model. Great Threads, a small clothing maker, can produce 5 products. We have shirts, different shirts, pants, skirts, and jackets, 5 products. And in this table, you can see other information. For example, for making any of these products, shirts, pants, etc., you need to rent a machine to do that. If you don't want to produce, you don't rent. But if you want to even produce one of them, you have to pay a fixed cost of $1,500, for example, for shirts. For this shirt, $1,200 for renting a machine to produce these shirts, $1,600 for these pants, and so on and so forth. The labor cost, these are the first one is the fixed cost, the labor cost, and the labor cost is actually variable cost. That means that if you don't produce any, you're gonna need zero labor. But if you produce, one shirt is gonna require 2 hours, or one whatever unit here we have. It's gonna require 2 hours. For the second shirt, we have 1 hour requirement labor. For pants, we have 6 hours. For skirts, 4 hours. For jackets, it's 8 hours. We see the cloth condition requirement. For example, for this shirt, we need 3 square feet. For this shorts, we need 2.5. This is short, is not short, sorry. For this short, we need 2.5 square feet of cloth. For these pants, we need 4 square feet of cloth. And for skirts and jackets, we need 4.5 and 5.5 respectively. The selling price for these products, you can see here, for shirts is $35 per shirt. For shorts is $40. For pants, $65, $70, and $110 for jackets. And you see the unit cost, which is also the variable cost. That means that if you produce even one shirt, it's going to cost you $20, plus the fixed cost that no matter whether you produce or not, you're going to have to pay it. How many, regardless of how many. So $20 for shirts, $10 for shorts, 25 and 30 and 35. So you see all these requirements, and we have actually limitation on this labor and costs. For example, we have only 4,000 labor hours per week or whatever, and 4,500 square feet of cloth. So that means that whatever you produce, you have to make sure that it doesn't exceed your cloth square feet available, or the 4,000 labor hour available to you. What is the goal? The goal, of course, is to maximize the total weekly profit. So you have to come up with the revenue, the cost, and then the profit. The cost is going to be the fixed cost and the variable cost. So the fixed cost of renting machines make this problem non-linear, because it does not, it depends. So if you do not make any, for example, shirts, you don't need the fixed cost. The fixed cost is going to be zero. But when you want to make one shirt, it's going to be $1,500. 2 shirts, if again, $15 million. Okay, so this is not kind of a linear relationship, right? So it's like a 0-1 relationship, kind of relationship. That's why this is a nonlinear problem in art, but we can actually kind of be smart and transform this using the binary variables to make these linear problems that we can still solve using simple examples. Okay, so this is how we would do it. So for example, if X equal to 50 shirts are produced, the total cost is 50. The total cost of 50 is $1,500, the fixed cost, plus $20 variable cost multiplied by $50 multiplied by 50 shirts. That's $2,500. The same goes for zero. So for example, the total cost of producing zero, if you actually rent it, would be like zero. But from 1, it would be 1,500 plus 1. So the total cost of 0 would be 0. The total cost of 1 would be 1,500 plus 20. The total cost of 2 would be 1,500 plus 40. So it's not a linear relationship here that we have. It's non-linear. The key idea is you want to use the binary variables to make this problem linear. So this is what we're going to do. If X is greater than 0, then Y is 1. That means that if we decide to produce shorts, for example, then we're going to go ahead and rent the machine, okay? And X has to be greater than 0. if we don't decide to produce shorts, that means if X equal to 0, then Y has to be 0. So, and this was one of the extension that we talked about it in the last slide of the last lecture. So we say that if the production constraint is X has to be less than or equal to the maximum shared capacity multiplied by Y, which is a binary variable. So if Y is 0, that means we don't want to produce any shirts, and then X is 0. But when Y is 1, that means if we decide to produce shirts, then X is less than the capacity. So it's kind of two conditions. X is either 0 or less than the capacity. So the right-hand side of this constraint, the maximum shared capacity, is the effective capacity, depending on the labor constraints and the class constraint. Okay, so whatever the minimum of those, the effective capacity, the minimum of the effective capacity of those. The maximum shared capacity divide the available labor hours, which is 4,000 hours, and class 4,500, by the labor hours and the cost required, the cost required by each shirt, respectively, and take the smaller value. For example, here we see that we have 4,000 labor hours available. For shirts, we need 2 hours of labor, so 4,000 divided by 2, that's 2,000 hours, and that's 2,000. And for class is 4,500 divided by 3, which is 1,800. Okay, so the minimum of 1,800 and 2,000 is 1,800. So the effective capacity here, or the maximum shared capacity, would be or 1,500 here. So the total cost would be 1,500 multiplied by Y plus $20 multiplied by X. Okay, so if Y is 0, X has to be 0 too, because of this. Okay, so if Y is 0, then you're not going to produce X. If Y is 1, then you're going to pay the $1,500 for ripping the machine. You're going to also it's going to take care of the fixed cost, and the 20 multiplied by X is going to take care of the variable cost. So this is how we formulate the fixed cost and variable cost. And using this technique, we actually transform a nonlinear problem to a linear problem by using smartly using the binary variables when this constraint. Okay, so let me actually open up the other Excel file to solve this problem. So after installing the solver table, if you have a desktop or a PC, you might also, like me, every time that open Excel, get a message that you didn't get it. That's because of the solver table add-in. And so you cannot open it on the protected view, so I have to reopen it again. Okay. Well, this is luckily open. Now we can show you. All right. So this is the data, the fixed cost manufacturing. I'm going to save this as something else, so I would not lose it. I'm going to actually do it somewhere else. Data to save. Okay. So these are our data. we have the same information that we had before. The product data, we have shirts, shorts, pants, skirts, and jackets, and the labor cost, the labor and cost requirement for each product, and then the selling price, the variable cost, and the fixed cost. And here we're going to create our decision variable here. So we have two types of decision variable. We have the Y decision variable, which is the binary decision variable that I showed you in the slide. And that's actually to help us to transform this nonlinear problem into a linear problem. And Y is going to tell us, okay, so if we decide to rent and produce, for example, shirts, then Y has to be 1 and X has to be non-zero. But if we decide not to produce, that means if we decide X is 0, Y has to be 0. That means that we're not going to actually rent the machine. So that's going to take care of the fixed cost here. So I'm going to make this my decision. This is Y. Rent equipment. Y variable. Just going to add this. You don't have to do that, but I'll just do it. It's going to make the name a little bigger. I can actually add it here. Y variable, which is X variable. Okay, so this is the X variable, this is the Y variable. And we have actually 5 products here. So we have 5 binary variable or Y and 5 actually integer variable. The effective capacity. So the effective capacity is, we're going to say X has to be either, let me show you this. This is how we formulate it. So we say that X has to be less than equal to the maximum shared capacity multiplied by Y. Okay? So X is one type of decision variable, Y is the binary decision variable. We need to find the maximum shared capacity, and actually that's the minimum value of the effective capacity. So let's find the effective capacity. The effective capacity is minimum of 4,000 here. Let me actually name these two. Okay, so I'm going to use I have to use the fixed value here. So minimum of labor hours by 4. Divided by, so that's the absolute value, the value, divided by the labor requirement here for shirts. And this value, the absolute value, divided by the cost requirement for shirts. So that's 1,500. Okay. Now actually I can drag this. Okay. So let's find the effective capacity. All right. So what else we need? We need you go back here. We need the X to be less than equal to maximum shared capacity multiplied by Y. Okay, so this is what we have to do. We want to say, I'm going to insert a symbol here, less than equal to symbol here. Less than equal to symbol. Okay, less than equal to. So you want to say these are X variable, okay? So X variable. X variable equal to less than equal to the effective capacity multiplied by Y. So this has to be multiplied by Y. I'm going to drag this down here. Okay. So now if I put any value here, this only can be 0 or 1. For example, 0, 0. If you change these y variables, your effective capacity is going to change. So also your x variable is going to change. Okay, this is just a random selection that I did. We're gonna change that. The solver is going to change that. All right, so this is going to be our constraint here. We also have other. We have to compute other things such as we need to actually compute the objective function. So the objective function, we want to maximize the total profit. So we need to compute the revenue, the total cost, which is going to be the fixed cost and the variable cost, and then compute that. Okay, so we're gonna compute the revenue here. Revenue, variable cost, fixed cost. Profit. So revenue is going to be the sum product of whatever we produce and the selling price. Okay. Right now is 0 because we don't produce anything. It's going to change. For example, say if it's 10 shirts, just a random number. It's going to change. Variable cost. So variable cost is going to be again the sum product of our decision variable, x decision variable, and the variable cost. So that's 250. By the way, this has to be all in dollar values. Fixed cost. Fixed cost is just going to be the sum product of the y variables and the renting cost. So right now we are producing shirts and pants. Like this can actually cannot be 2. It has to be 0. This can be, for example, non-zero. So we are actually producing skirts and shirts. So we have to rent actually the machines for shirts and skirts, which is 1,500 and 1,500. And the profit would be revenue minus variable cost minus the fixed cost, which is 19. Right now it's negative, but we're gonna make it positive. Okay. What else do we need? We also need to make sure that the labor and the class requirement or the class capacity are not exceeded. So we need to compute those. How much labor we have used. So this is going to be also a sum product of the x variable and the labor hour requirement. And for class same, x variable and the class requirement. So these values has to be less than equal to the capacity that we have. Okay, I'm going to name this used, available, okay, so let's see what we have here. We have use only have topics. right? Okay, looks like we are ready for solving the problem using Solver. So let's go to Data tab, Solver. We are maximizing the profit. So it's maximized, and the profit is here by changing these values. We're going to add the constraints that these x variables must be less than equal to the effective capacity. Add. The other constraint is that the used resources must be less than equal to the capacity that we have. We have another constraint, and that constraint is that these has to be binary. Okay. So we have to add these three constraints. Not sure why this has not been selected. These two. We could name both of these as decisions. Okay. So I'm going to make sure that the variables are non-negative, and I'm going to select the simplex LP because we actually need simplex LP here. And I'm going to go to options, and because we have integer variables here, I'm going to make sure that this is 0, so it finds the best optimal solution. I click OK here, and I'm going to click solve here. So it found the optimal solution, and our profit actually became positive. It's 54,000, and we have decided to produce shorts and jackets only. As you see here, we have actually non-integer or non-whole numbers variables here. You can't really produce 965.5 shorts or 379.3 jackets. So what you could do is you could either round this up or down, depending on you have to make sure that the constraints is not violated. Or you could actually go back to Solver and add the other constraint, and the constraint is that this variable has to be integer. So I add that constraint, coming back here. Look at the solution. The solution that we have is we have non-whole numbers or non-integer numbers, and our profit is 54,614. I believe by changing this, by enforcing this constraint, our profit is going to go a little bit down, but not by too much. So it went from 14 to 05, which is about $9. That's almost nothing. So this is our optimal solution. All right, so we are actually at the end of the first session. So we're going to actually take a break, then we're going to come back. All right, we are back again. Let me share again what we have in Excel. So this is the problem that we solved, the manufacturing problem, which was originally a non-linear problem, but we actually got it smart and used the binary variable y to get rid of the non-linearity in the problem and model it as a linear problem here. So as you see here in our optimal solution, where actually x is 0, y is 0, and where x is non-zero, y is 1. So for example, 0, 0, 0, 0, 0, non-zero, 1, non-zero, 1. That means, okay, if you want to produce jackets, you need to rent the machine. If you want to produce the shorts, you need to rent the machine. If you don't want to produce pants, do not rent the machine. So that's what you have to do. Okay. In Solver, we talked about this one. In the optimal solution, note that y should be 1. We talked about this one too. Okay, something about Mac. Those people who have Mac. Excel actually for Mac computers may not produce the correct answer. May not. May work, probably. There is no way around that. Sorry about that. If it doesn't work for you. If you're a Mac, you're working with Mac and it doesn't work, that's because of the problem with Mac and Excel. It's not because of Excel itself, because it works on PC computers. So let's do some analysis here, sensitivity analysis here. So we want to see how does the solution change if the number of units produced are also required to be integer. That is what the change actually about $9 when we require the X variables to be integer. It dropped. If you remember, it dropped the optimal solution, the total profit from 54,614 to 05, which is about $9 down. So let's do the sensitivity analysis using the solver table. We want to see there are a lot of inputs here that we can actually study the impact for example, the limit on the labor hour, the limit on the class square feet, total class square feet that we have. We have the all information about the selling price, variable cost, and fixed cost for the 5 products. So any of these can be inputs that you can manipulate and change and see the sensitivity analysis or the impact on that on the outputs, the decision variables, and the optimal solution or the total profit here. So for this specific example, suppose that we want to see the impact of selling price for skirts and how would that change our optimal solution if it changes from $7 to $100. So right now, for skirts, the selling price is $70. We want to see how would that change, and we do not produce actually any skirt. That means that it's not worth it to sell it, to produce it and sell it. So we want to see at what point or how much the selling price for a skirt should be so that it would actually come to the table. That means it would be recommended to produce it. It would come to our optimal solution. Okay, because this is, if you remember, because this is actually an integer problem. When we solve it, we do not get the sensitivity analysis report here. So that's why we cannot actually use that to do this analysis when we have to do it manually here. So we're gonna change the selling price for skirts from $70 to $100 by an increment of $5 and see the changes that it would make on the decision variable and also for the objective function. So let's do that. I'm going to go to the solver table, run it, and click OK. We want to run a one-way table, and the changing value here is the selling price for a skirt. Skirt price. And we want to change it from $70 to $100 by increment of 5. And what we want to see is we're not gonna look at, we don't really need to see the impacts on y variable because they are just 1 and 0. And wherever x is 0, y is 0, and wherever x is not 0, y is 1. So we don't need to include them in our output. So I'm just going to include the x variable and the profit, the objective function. Click OK. So I'm gonna it's gonna run a bit. Gonna take a little bit of time, and then it's gonna produce this sheet here. So this is the skirt price here that you see on the left side, And the price is gonna change from $70 to $100 for increment of $5. And these are the 5 products that you see here. I can actually copy and paste these here to make it easier to read them. Now these are so shirts is never actually in our, because we actually don't change it. The only thing that would actually have to be is the skirt. So a skirts is not in our optimal solution. And if you look, it's interesting because the shorts are in our optimal solution. Stop share.
Professor, I think you're muted.
Oh, okay. All right. So I have to say this all again. Thank you for reminding me. So if you look at our decision table here, when the selling price for skirts is $70, the optimal solution is to produce shorts and jackets. Okay, jackets and shorts. But when our selling price for the skirts jump into $90, it actually becomes part of the production plan. And not only that, but it also tells us that do not produce anything else. Do not produce jackets, nor produce shorts or anything else. Just produce skirts. And because it's the most profitable item on the menu. So if we actually plot this graph, which is the profit versus the skirt price, you see that when the selling price for a skirt is $70 or $75 or $80 or $85, the profit doesn't change. The objective function doesn't change, or the optimal value doesn't change because it's not on the menu to produce. But when it's $90, we are producing and selling skirts, and that's the only thing that we sell. And that's when you increase the price, our profit's going to go higher and higher and higher. So this was the sensitivity analysis that we wanted to do. All right, so one actually important note here, in your modeling of any programming, optimization programming, is either linear programming, continuous linear programming, or integer or binary, whatever model you have. Try not to use actually if function from Excel in your decision variable. It's okay to use it in any input or medium calculation or pre-processing table or whatever, but do not use it in the decision variable table or decision variable column or row or whatever you have. Do not use f or other function in that for decision variables. But it's okay to use it in other, in between tables or in between values. Right. And one more thing, if problem is too hard that there is no other way to not use if a statement in decision variable, then this is going to be a non-linear problem, but you're using the if for other functions, and then we cannot solve it using simple XLP. So you're gonna have to use evolutionary algorithm in the solver dialog. So this is another chapter that we're gonna talk about it later on. So that's another problem that we are done with. We're gonna move to next problem. The problem part 3. Right, integer problems, optimization model with integer variables, part 3. So this is another type of integer models, or models with integer variables. We call them integer programming models. It's set covering models. Suppose that each member of set 1 must be covered in some way by a member of another set. For example, you have a county or a city, and then you want to locate a certain number of locations for installing a police station or an ambulance or whatever other city service that would service the city in its vicinity, and there's like a limit for that, say 1,000 miles or 100 miles or 10 miles or whatever number. There's a limit to that. And so what you wanted to do is to locate those locations to install those services to cover that set, whatever it is, if it's a county or whatever. It's a city, it's a town. And you want to minimize either the number of stations or you want to some other objective function. So this is called the set covering problem, because there are two sets, and from one of the sets you want to pick so that it would cover the other set. Okay, so we have the examples are the fire station siting. So you want to install fire stations in some certain places within a certain vicinity of each part of the city, so that within a given number of fire stations, because building a fire station is expensive, and also building a police station or any other services is going to cost us citizens money and our taxes. So you would want to, the city would want to, and us also would want to minimize the cost of spending for these. So we're going to optimize it. So what we're going to do is we're going to find the best location so that for this fire station or for police station or for ambulances, for other services, that with the minimum number of stations, we can actually cover the whole city or the whole county. Okay. So set funding in the fire station example, there are two sets in all the examples. Set 1 here is the all towns in a given county. Set 2 is all potential fire stations in that county. And a fire station site covers a town if a fire truck from this fire station can drive to the town center within X minutes. This is the condition that I told. What is the goal? The goal is to minimize the number of stations required to cover the city or to cover all the towns in the county. Other applications, again, it can be for any other type of service. It can be for police station, it can be for ambulances, or etc. etc. So this is called the set covering model. So you're going to have why this is an integer model, because to build a fire station at a certain location is either 0 or 1. Either you built it or you don't build it. So that's why it's a binary model, because just two decisions of 0 or 1, build or not build, use or not use. So let's see another example of this kind of the set covering model. It's a hub location for Western Airlines. Okay, so hubs for airports, as you may know, used by airlines to consolidate passenger traffic and flight operations when you have like a huge geographical area, such as like a big country, especially. They serve as transfer or stop over points to get passengers to their next destination. That also would work for international flights. Western Airlines is designing a hub system for the US flights. Suppose that the airline flights serve a dozen of US cities. It serves Atlanta, Boston, Chicago, Denver, Houston, Los Angeles, New Orleans, New York, Pittsburgh, Salt Lake City, San Francisco, and Seattle. These are a subset of these cities. These serves as a hub. So these are the potential hubs, okay? But we don't want to use all of them. That would cost us a lot of money. So we want to see, okay, with the minimum number of these hubs to build, we want to make sure that the whole country is covered, or all the area or cities are covered. Okay? So we're gonna set a coverage criterion. Hubs connect flights to and from cities that are within, say, 1,000 miles. So this is the condition. Okay? So a city is called covered when its location to a selected hub is 1,000 miles air mileage. This is not like road mileage. Air miles, that's different. So we're going to have a data for this, and the data is going to be the distance matrices from all of these cities to each other. So for example, for these all cities, whatever number they are, to each other, because these are the main airports. So when you select some hubs, there are some of these airports that are covered by those hubs when the selected hub's distance to that specific airport is less than or equal to 1,000 miles. Okay, we say that it's covered. That's the coverage criteria. What is the goal? We want to minimize the number of hubs to cover all these 12 cities, major airport cities. This is also kind of non-linear because we have a condition of the covering and not covering. Is 0 or 1. So we say that, and it depends on the distance. So we say a city is covered again if the distance between that city and the hub is less than 1,000 miles. So it's a 0 or 1 binary actually coverage matrix. So it's 1 if the city is covered by a potential hub, it's 0 if it's not covered. What are the constraints? Each city must be covered by at least 1 hub. We want to make sure that every major cities that out of these 12 major airport cities are covered by at least 1 hub. It's okay if 2 hubs cover a city, but it's not okay if a city is not covered by any hub. Okay, so that's the constraint, and the only constraint that we have. Let me go ahead and open up the Excel file, and the Excel files are available for you on iLearn, and you are able to download them and work with them. So the data is just the raw input data that we can use to build the model. So good. Try really hard. Yeah, for some reason it doesn't open. Try again. All right. Let me share this with you. So this is the data file. As you see here, we have the Western Airline. I have named the sheet. This is the problem, Western Airline Hub. This is the input data. We have one important input data is the mileage. standard, which is 1000. You can change it. And there is this matrix of the 12 cities to 12 cities, each city potential hub cities on the column and row and from each other. Of course, Atlanta, the distance to these are the distances, the air distances. So Atlanta to Atlanta is 0. The air distance to Atlanta from Atlanta to Boston is 1037 miles, and this is actually the same from Boston to Atlanta. So that's why you get the same number on the column as well. So these numbers from Atlanta to every other city are the same as these numbers from those cities to Atlanta. Okay, so this is what it means. And each city distance to itself is 0. Okay? So that's why you get the symmetrical matrix here. Okay. All right. So this is the inputs, and these are the key to interpret the cities. ATL stands for Atlanta, Boston, etc., so on. So now let's go ahead and try to model the problem. So what do we need? First of all, we need a coverage attribute matrix. Okay, potential hub and potential coverage matrix. So I'm going to create another intermediate or in between table here, and also the decision variable. So this is going to be the air coverage matrix, whether a potential hub would cover a city or not. Okay. So I'm not going to call it a distance. I'm going to call it air coverage. Name of the cities are going to be the same. Same for each row. Okay, and here we're gonna build our matrix, a coverage matrix, and here we're gonna build our decision variable. I'm gonna copy and paste the hub names again here, so you would know that whether a hub is selected or not. So this is going to be our decision variable. Not this one. All right. And also the objective function. So the objective function is going to be the total hubs selected. So that's going, because these are binary variables, just the summation of these. Okay, so I'm going to put it here. Say the number hubs, number in all hubs, number of hubs. And that's going to be a summation of all of these values. And this is going to be our output. So what else do we need? When a hub is selected, a potential hub is selected, we have to make sure that every city is covered. That's the only constraint that we have. We want to make sure that every city is covered by at least one hub. Okay, so here we're going to actually implement that constraint. I'm gonna create a column here called covered by. And covered by is just going to be the summation of these values. These values are going to be 0, 1. So If, for example, Atlanta is covered with any of these hubs, these are potential hubs, then there's going to be at least one here, and the summation of that is going to be 1 or more than 1. So we want to make sure that this is actually greater than or equal to 1. So I'm gonna put a symbol here, greater than or equal to symbol here. And this is the required coverage, which is 1. And this is going to be an input. So I'm going to use, we could say that, just printing this up. For the sake of safety, we want to make sure that at least 2 hubs at each city are covered by at least two hubs. So this can be 2 or 3 or whatever numbers. But right now we're going to have it just 1. All right. So how to figure out now these values? So Atlanta is going to be either covered or not by Atlanta if Atlanta actually is a hub and the distance from Atlanta to Atlanta is less than this mile limit. Let me actually select this and make it name, range name, and decisions. This is decisions. The number of hops is also arrangement. So we're gonna say if Atlanta is selected as a hub and the difference between this city and Atlanta is less than 1,000, then that's 1. Okay, so it's going to be if this is 1 and this is less than this value, then 1, otherwise 0. Okay, so let's see if this is correct. This is gonna say, so this is what we want to say. We want to say if Atlanta is selected as, or let's say another, if Boston is selected as the hub, that means that if this value is 1 and the distance from Boston to Atlanta is less than 0, we would make it 1, otherwise 0. Okay. Right. So I'm gonna say if the distance is less than the city limit, line limit, 1, otherwise 0. Okay, so Atlanta, of course, is going to be covered by Atlanta. Atlanta is going to be covered by Houston. Atlanta is going to be covered by the New Orleans, New York, Pittsburgh, etc., etc. And now we can actually drag this down. So these values shows if for each column, for example, for let's interpret this. That means that if Salt Lake City is selected as a hub, it's going to cover them. And this is what it means. And this cannot be actually the sum now that we did this. This actually has to be now, if Atlanta is selected, then this value. So it's going to be the sum product of these decision variable. If the hubs, if any of these hubs is selected, then put a 1, otherwise put a 0. So it shouldn't be sum, it should be actually the sum product. So I'm going to make it sum product. Sum product of the decision variable for each column and each row and the values. Make sure that this is correct. I'm going to drag it down. Make sure that this is correct. Yes, all right. So now it makes sense. So we would say that, okay, for example, I'm gonna make Denver as a hub. So Denver is a hub, and it's gonna cover, of course, gonna cover Denver. It can be a hub for itself, and it can also be a hub for Salt Lake City. So if Denver is a hub, then Denver is covered. Salt Lake City also is covered. If Atlanta is a hub, Atlanta is covered, of course. Chicago is covered. Denver is covered by Salt Lake City, by itself, and also Salt Lake City. Also going covered by Denver. Houston is going to be covered by Atlanta. New Orleans is going to be covered by Atlanta. New York City is also going to be covered by Atlanta. Pittsburgh is also going to be covered by Atlanta. Salt Lake City is going to be covered by Atlanta. But as you see here, some of these values are 0, which violates our constraints. So we want to make sure that every city is covered. So this is not a feasible solution. I have to make another city to cover them. From Seattle, San Francisco, LA, and Boston. So I don't think picking San Francisco would cover Boston, and it does not. So I'm gonna have to pick Boston as well. So the solution that I got here is feasible, but it would require, as you see here, would require actually 4 hops. Okay, it would require 4 hops. And also, as you may see here, some of the cities are covered by 2 hops. For example, New York is covered by 2, Pittsburgh is covered by 2, Salt Lake City is covered by 2. All right, so that's all we have. I think if you have everything, you have the decision variable, the objective function, we have the constraints, and everything is ready to, let's go ahead and solve the problem. So we're gonna go to, oh, okay, interesting. I don't see actually solve the group here. That's why it didn't start to open. Let me save this as another thing so I wouldn't lose it. I'm not sure if you see, you probably can see actually my screen here. Under data, I don't see the solver. It disappeared. I don't know why. So I can't solve this. I have to close it and reopen it. All right, so sorry, I don't have it. Somehow, for some reason, solver disappeared, and all other inputs from that group was disappeared from Excel. I'm gonna try one more time. It's unbelievable. It is in my add-ins. the analysis tool pack is in my add-ins, so there's nothing I can do. It shows here that it's actually should be in Excel, but it's not.
Professor, in your top ribbon, if you go to help and you search solver, do you have the option to pull it up?
Um, where is it? I'm gonna share the screen here so you would see what I'm placing here. So as you see here, I don't have the under data. I don't have the. So you said go to help here.
It would be, sorry, I'm on a Mac, so our views are a little different, but there should be a way that if you search for within help, oh, up at the top where it says, it's got the top bar up where it says autosave off, you have save. If you go to the search bar where it says search parenthetical alt plus Q and you type solver in, the tool should come up.
Here.
Yes, in there.
Solver. It says add-ins. Analysis toolbar is okay. It should be here, but it's not. Solver.
What works for me is if you go to the options and go back to add-ins and then
Yeah, I did that. It doesn't. It says that it's actually installed. So if you go to add in here, it shows that these are the active application. It's here. The analysis
Right.
toolbar is already in here.
yeah, I
So
get the same thing, but you gotta reload it from the file. So you gotta go to browse and then go to wherever your solver table file is. I know in the instructions you had to save it in like Microsoft Office under like program files. I'm not sure where yours is at, but usually when I go back to the main file, it'll add it in there.
Let me actually uncheck it.
I tried that before too, and that one doesn't work.
It doesn't work.
Nah.
Great. Doesn't even show the table. Analysis toolbar, solver add-ins. Okay. Oh, it looks like it's doing something. Not sure. Oh yeah. All right. Okay, great. Oh, I have it back here. Okay, good. I forgot if I have named anything here. Probably I did. I can go to formula. Thanks everyone. Yes, I have the decisions, the mile limits, the number of hops. Okay, I don't have the covered by. I have to name all these two. So I'm gonna name these two columns for the constraint that we need. So if solver disappeared from you, it worked for me, might not work for you. So what I did actually, I unchecked it and I checked it again, so it came back. I'm not sure if you know in general, but that was really weird. I never had this experience. We want to minimize the number of hops, minimization. And the decision variables are these 12 cities, and the constraints are these covered must be greater than or equal to these values, and our decision variable has to be binary. Click OK. I think I put everything here. Number of hops, decisions covered by required decision binary. Make sure that these are non-negative. I'm gonna make simplex because we have binary variables here. I'm gonna go to options. I'm gonna make sure that the integer optimality has 100% or 0 here. All right, I'm gonna go back. the solution that I had just randomly generated would require 4 number of hops to cover all these cities. And the cities are Atlanta, Boston, Denver, and San Francisco. So I click solver to make it find the optimal solution. The optimal solution here is actually 3 hops, and it's Atlanta, Boston, Salt Lake City. And we still have a couple of cities that are covered by 2 hops, more than 2 hops here. New York is covered by 2 hops. Pittsburgh also is covered by 2 hops. Atlanta, Boston actually both can cover. All right. All right, so done with that. So let's see what we have here. We need to do some analysis here. There are multiple optimal solutions. Okay, so here also we have multiple optimal solutions. So if you actually get a different solution that I got, but you still have to have 3 cities. If you get 2 cities, then it should be impossible to get 2 cities. So you should have 3. The number of hops should be 3. You may have actually different cities that I have, like Atlanta, Boston, and Salt Lake City. You may have a different city, but it should be these 2. I mean, number of hops should be 3. So right, we can actually try Houston, New York, and Salt Lake City. So let's see if that will work. New York, Houston, and Salt Lake City. Yes, that also works. So this is also an optimal solution that we just solved it. We didn't solve it, but it's another optimal solution that had 3 only hops. So we want to do a sensitivity analysis. There is here a major input, very important input. These are all values that don't really change. These are the air mileage. But what can change is actually this with the assumption that you cover a hub when it's close by less than 1,000 miles. And this is a very important assumption. So you want to do like a sensitivity analysis here, because this is an integer model. We cannot, our the solver doesn't give you actually the sensitivity report. So that's too bad, but we are lucky to have, the table is gone now. The solver table is gone. All right. I have to go get that. Okay, sorry for anything that happened here. My kind of fonts. Anyway, this is our lecture today. I have uploaded assignment 6, assignment number 6. Assignment number 6 is have kind of a touch on this second problem that we saw here, the air mileage problem. It's going to ask you to add 2 more cities, Winnipeg and another city, and Winnipeg in Canada. What you have to do is to find the air mileage. Make sure that you find not the nautic air mileage or the kilometers, because it's in Canada. They have like a standards, international standard, so you would use kilometers. So make sure that when you Google it, Google for air mile or air distance mile, say Atlanta to Winnipeg, and it's going to give you a couple of numbers. Make sure that you pick the mile one, not the kilometers or the others. So you would have to kind of extend this problem to be able to solve the second part of the assignment 6. The first part is not related to the air hop problem. Any question or anything? All right, thank you very much, everyone. Have a great night.
Thank you,
I'll
Professor.
see you